Good afternoon, everyone, and thank you for this opportunity to present my work today here at this event. So I will be talking about how to use NXCT simulation combined with generating the images or synthetic images of surfaces to extract looking through like the surface roughness of AM parts for additively manufactured parts. So the use of AM is on the rise in every sectors, medical, automotive, etc., because it offers some incredible versatility for creating bespoke design of one-off prototypes. But without the correct finish, those components may fail. The aerospace and defense industry have already adopted AM, but they must make sure that the finish of these components fulfill all their requirements. Here we have, here we have two. Here we have one part that was 3D printed and applied some surface finish treatment. And we look here at high resolution, how the surface treatment have affected the roughness. So this is before the treatment is applied on the surface, and this is after treatment is applied on the surface. So the surface texture of this internal features needs to be controlled for different reasons. Rough surfaces are prone to initiate cracks, and as well rough channels will change the fluid transport in them. So to be able to control the surface texture, we need to of AM surfaces. We need first to be able to measure the surface roughness. Traditionally, the surface roughness is measured using instruments such as a profilometer. So you have a stylus that you pass through the surface, and the stylus will then be able to detect or give you a read of or an idea of your surface roughness. So when it comes to a compact measurement system machine, because of the hardness of the stylus, sometimes you can scratch the surface. And as well, you have some limitation on the resolution, and that's the limitation is dependent on the diameter of the stylus head. Here. The non-compact measurement system, using, for instance, a laser, will give you better resolution and will not affect as well the surface texture conditions. But the problem will come with, for instance, when you have a laser, is the surface finish will place there, for instance, will have some refraction and other problems. Oh, thank you. I don't know who did that, but so these different surface roughness parameters that were defined many years ago. Those parameters help to give you an idea on the surface roughness. So here I have listed some of them, but mainly in today, oh, sorry, we will be focusing on the SA here, the roughness average, the mean high. Okay. So we understand that to measure surface roughness, we have traditionally the tools or the techniques. But when it comes to additively manufacturing, we have as well create internal surface that can be accessed by probes. And so usually a researcher, what they will do, they will cut open the part to so the probe will be able to access that part. but obviously industry can't use that method. Obviously, you don't want to destroy each time your part before and then test it, then you don't have any more parts. So this is why X-ray CT is the technique. It's the only valid non-destructive method. But when it comes to X-ray CT, you have as well other questions to answer, and mainly about surface determination method. We know that will affect, will have significant effect on dimensional information that you will be extracting. So basically, everything is about segmentation here. As well, we all know that when you do some X-ray CT, you have a lot of artifacts and noise at the surface, and that makes as well the interpretation of those data more complicated. So this is an example of the additively manufacturing parts. So again, the outer part, obviously, we could have used a profilometer or another traditional instrument or traditional method. But when we want, if we want to access the internal surface roughness, we don't have here the tools. So this is why the use of X-ray CT here. So now let's come to synthetic data. So they have quite a lot of interest because they permit to develop. They help to the development of data processing methods, analyze as well the uncertainties, and estimate so various measurements artifacts, as well creating I would say not fake but artificial data, so synthetic data. You are able to very quickly generate data for machine learning and deep learning. And that will help you for validating as well a segmentation technique or image processing and analysis workflow. I have looked into methods or already available way to generate synthetic surfaces. I found the Guidion, which is metrology software to measure surface metrology software. It offers the possibility to create synthetic surfaces. Here an example where you have 3 different surfaces generated with this software. Another software or plugin developed in MATLAB permit to generate how we call random rough surfaces. The problem with all those solutions is they cannot generate a 3D volumetric data set. They will work only on flat surfaces and doesn't work for enclosed or enclosed surfaces as what we have in additively manufacturing. So this is why I'm proposing today a new plugin based on ImageJ to generate surfaces, synthetic surfaces. Okay, so in the next slide, I will present the next slide will be presented in 4 parts. First of all, the creation of binary synthetic images with a cuboid hollow shape with different surface roughness. Then those synthetic data will be virtually CT scanned. Then we will determine the surface of those different images using machine learning approach and hysteresis thresholding. And we will compare all those other measured surface roughness to the ground truth, here the synthetic images. Okay, so this is the GUI of the how we call it of the plugin. At this stage, it's still a macro, so it's really written in ImageJ1 macro language. But I plan to move it to plugin or maybe even like So that's what I have at this stage. It's very simple. So you have at the top parameters to adjust the surface roughness. Then you can change as well the sample size, and so like the hollow size. And you can adjust as well the material dimension or size surrounding this hollow shape. Okay, this is one create or generated synthetic data. So I have put letters on the top. You can see T, L, R. It's for orienting the volume. I do like this. So you can see L, the face L and B are rough. And I will animate this, and you will see the face T and R have much less roughness compared to the face L and R. And that's here this hollow shape we are interested in. At the bottom, you have this table. So this is summarizing the settings I have used in the plugin previously. Okay. Yeah, so this is. Here you have a 3D view to see the different faces of the hollow shape. So in the next one, I have modified the amplitude and what I called here interval. I've increased them. And you can see that's have changed the internal surface properties here. Okay. So I haven't, so this is sample 20. And sample 100. So I kept always the same hole size and the same image size. So here I have I placed the amplitude and interval to 10 and 10. And obviously that have increased tremendously the surface roughness here. So this is how I generate synthetic data. So here it's sample 100. So I have generated 100, but I have analyzed only one sample. So all those samples are then converted to meshes, and I used the artist simulator with those parameters to scan them. And here you have so the meshes here that are generated out of the synthetic images. This is a virtual scan on sample number 1. This is one slice. And this is sample 100, one slice as well. Here I try to compare, correlate on the left, the synthetic data, and on the right, the, how we call the virtual scan, and it's correlated pixel by pixel. It's going a bit fast, but yeah. Oh, let's see. And then we can like find the structure on the left and the right. So after all this, we wanted to determine the surface on the virtual CT data. So we used so first method we use is hysteresis thresholding, and the output we have is this one. For instance, this is a single slice on the The second approach is using machine learning and Weka software on Fiji, MSJ. We have defined 3 regions. In green, that's the material surrounding the hollow shape. In purple, that's the air. And in red here, you can see that's the surface, 1 pixel surface. So we have used our ground truth image to label label here the image, and we have at the end a classifier classifier is used on the rest of the on the rest of the images. So here I present the 3D surface plot of the top and the left face in sample 1. So just to remind you, the top face have very little surface roughness, and the left face as well as the bottom face have much more surface roughness. And that can be actually seen on in here. That's our ground truth. That's the synthetic images, and that's the simulation here. Here we compare the different segmentation technique all together on sample 1. So you can see the hysteresis thresholding for surface determination here, a machine learning approach, and that's the synthetic data or our ground truth. We can see that that's the scale give you like the maximum amplitude or the maximum height seen. So for synthetic data, okay, we can see like similarity between machine learning and hysteresis thresholding for the left face, but obviously there's a huge, quite big difference compared to the ground truth here. And here that's some data. So from there, we, as explained, we can measure a few parameters. Here I have measured the SA, and you can see that basically that's the ground truth. We have an SA of about like 31 pixel, but what we measure for machine learning and hysteresis is much less compared to the reality. Obviously the segmentation technique and scanning will affect what we can I mean like affect the detective sorry. We'll have an impact here on what we measure as surface roughness. Okay, the next step will be to use deep learning, but here we need to collect a bit more data and as well have different data. Sorry. For instance, change the X-ray CT parameters and as well the different material. We have employed aluminum previously, but we think on using different material as well. So today we proposed a method to analyze surface roughness and evaluate the segmentation technique. We correlated the surface roughness of artificial data on its virtual CT. So the next step as well would be to use the synthetic data to fabricate real parts and compare real X-ray CT of real parts versus virtual X-ray CT. And here for conclusion, I mean, obviously simulation offers the possibility to do quick and cost-effective X-ray CT images. Synthetic images offer here the possibility to have large number of samples with different surface roughness, and those synthetic images can be considered as ground truth here. And we hope to combine those two for creation of a deep learning model for segmentation and extraction of internal surface in AM parts. I wanted as well to take the opportunity to mention a bit of, to talk a bit about NXCT, if I have 2 minutes, yes. So NXCT is a hub where my facility, the Henry Mosley, is part of. We offer free point of access, up to 3 days free point of access to our instruments. We have about maybe 20 instruments between us and our partners. So please take the opportunity to request access, free access to the instruments. Yeah. And finally, as well, to mention the soon opening of the digital imaging lab, where we have about 20 workstation with a lot of RAM, amazing graphic cards, access to Aviso software, and other software that hopefully could help you solve some of your problems. So thank you very much. And if you have any questions, please.